In this video we're going to have a look at the structures of some aldehydes and ketones. Now aldehydes and ketones both contain the carbonyl group, and the carbonyl group is a trigonal planar carbon with a double bonded oxygen. The general formula for aldehydes and ketones, because they've got some level of unsaturation, is CnH2nO. So for every carbon there are twice as many hydrogens and an oxygen. So the functional group in an aldehyde is that we've got this carbonyl group, and the carbonyl group's on the end carbon, and therefore the final atom is a hydrogen, and there's just an R group, a chain of carbons on the other side. Whereas in a ketone, this carbonyl group finds itself in the middle of the chain of carbons, and so we have R groups at either side. Now these R groups could be the same or they could be different, so we could put a little dash there to represent that it's a different R group. So pause the video now and see if you could draw out some aldehydes and ketones from their names. Now remembering that if it ends in al, these are the aldehydes, so we're looking for the RC double bond O with the H. If they end in one, we're looking for ketones with the C double bond O in the middle of the chain. So pause the video now and have a go. So we should have got something like this for our aldehydes. What you want to be careful of is looking at how you're drawing them and not accidentally putting an extra hydrogen where the double bond is. The thing you might notice is that all aldehydes have this little bit in their structural formula, this CHO. We always write the H before the oxygen so that we're not confusing them with alcohols, because if we wrote O then H, we might confuse them with that alcohol structure. It is very unlikely that you will ever draw a skeletal formula for methanol, as it really doesn't simplify things a lot. It's a little bit confusing, but you can see the structure there. Remember, in the skeletal formula we do not show the carbons and hydrogens, but we do show any other atoms. So pause the video again and have a go at your structures of your ketones. So you might have noticed that we haven't got a methanone or an ethanone, because to be a ketone then the C with the double bond O must be between two carbons, so we can't have them smaller than 3 in a row. Neither of these two ketones need a number, because the second carbon along is the only one that could have the double bond O. In butanone you could do it from the other side, but it would still be carbon number 2. Notice that now to show in the structural formula that you've got a ketone, you've got a CO in the middle. You'll notice that propanone and propanal have the same molecular formula but a different structural formula. So propanone and propanal would be classed as functional group isomers. Remember that that is a type of structural isomer. So we had propanone and propan. Now what about butanone? Could you draw its functional group isomer, which would be butanal? So we've got butanone and butanal. Both of these are C4H8O but have different structures. So take a couple of minutes and think if you can find a pair of functional group isomers, a pair of chain isomers, and a pair of position isomers with the molecular formula C5H10O. These are some of the possible answers. There are others. So I've chosen to draw a 1, 2, 3, 4, 5 carbon chain, so pent. Single carbon-carbon bonds, pentan, and then it's an aldehyde because it's got double bond O at the end. On this side I've still got the 5 carbon chain, but it's now a ketone, which we know is an ONE, but we need to say where the ketone is. It's on number 2 in the 5. And for my chain isomers I've stuck with pentanal just like above, but I've changed the chain length to go for 2-methyl, running out of space there, butanal. You could have also gone for 3-methylbutanol. Methylbutanol is a chain isomer of pentanol. So you could have also had 3-methylbutanol, or dimethylpropanol is also a chain isomer of pentanol. Still an aldehyde but different chain length. And then for my position isomers, I've gone for pentan 2O, and I've moved the position of the functional group and made it pentan 3O. Again, I could have